All right, welcome back to Statistical Analysis in Psychology. This is week 13, class 1, and we're going to continue our look at chapter 8, Introduction to the T-Test, Single Sample and Dependent Means. Now, last time we met, we introduced the necessity for the T-Test, and we started off with one version of it, the single sample T-Test. Today, we're going to take a look at another version, which is the Dependent Means T-Test. So thank you for joining me on this day 3 of our face-to-face shutdown. And we're going to continue on with our look at real-world statistical tests, the statistical tests that are used in real-life situations. So no more assumptions made that are unrealistic. We are now dealing with real-world situations, and today is going to be the t-test for dependent means. Now, before we continue with this, just a reminder that we are starting to use statistical packages for statistics, software packages specifically designed for statistics, and the one that we're using is called SPSS. So if you haven't already, make sure that you have begun to access SPSS through the IU Anywhere service. So go to OneIU, search for IU Anywhere, log in using your student account, and you will be able to use SPSS from home, from your shutdown bunker, as long as you have internet access. So it might take a little bit to set up. It might take a little bit of contact with the IT help desk at IUSB in order to get everything working. However, this is going to be the solution that we're going to use so that you can access SPSS at no extra cost to you. So make sure that you're accessing this important resource through IU Anywhere. Check the previous lecture video if you need to know some of the details on how to access that. But definitely make sure, because we're going to need SPSS going forward. You will not be able to complete the rest of this semester without learning the skills in how to apply this statistical software package. All right, so what we're going to do today is we are going to take a look at dependent means t-test, and we're going to do it by taking a look at a study that looked at the effects of timeout. So prior to a lot of the work on timeout and the effectiveness of timeout for changing behavior, if you wanted to change a negative behavior in a child, positive punishment such as spanking was what was typically used. However, studies have shown that timeout, putting children into timeout as a punishment for poor behavior, is much more effective with fewer side effects than corporal punishment such as spanking. So the question we're going to take a look at today is that studies have shown that this is effective for changing children's behavior, but is it effective for changing adult behavior? Does timeout work for adults as well? So that's what we're going to take a look at today as we explore dependent means t-tests. So we're going to introduce the idea of a t-test for dependent means, doing a hypothesis test with a t-test for dependent means. And then we're going to launch into SPSS to see how you actually can do that using that statistical program. And then I'll mention the homework assignment and where you can find some extra practice with SPSS so that you can develop those necessary skills. All right, so we're going to dive right into our in-class practice demo problem. So let's begin with a description of this problem. So I will read from the description right now. So placing children in timeout can be an effective form of punishment. Research suggests that this same technique can also be effective for adults. In the study, participants were shown a series of colored shapes and had to classify each stimulus into 1 or 2 categories. Each correct response was rewarded with a nickel, and each incorrect response was punished by a timeout period of 5 or 10 seconds. During the timeout, no stimulus was presented, and the participants had no opportunity to earn more nickels. So if you made a mistake during this experimental procedure, you were put into timeout for either 5 seconds or for 10 seconds. The dependent variable was the overall level of accuracy during a series of trials. So during each series of trials, they measured how accurate were these individuals, how few mistakes did they make. And in each block of trials, the individuals, the subjects, would either be experiencing a 5-second timeout or they'd be experiencing a 10-second timeout to see how that affected their accuracy. So the dependent variable was the overall level of accuracy during a series of trials. Assume that each participant completed a series of trials using a 5-second timeout period. And then those same participants completed another series of trials using a 10-second timeout period. Data for a sample of 9 participants are as follows. We're going to see if the data indicates a significant difference, and we're going to do a two-tailed test with an alpha of 0.05. So we're doing a non-directional test because before we even begin this experiment, we have no good reason to assume that the 10-second timeout condition will lead to higher accuracy because of the effects of longer timeouts, or will the 5-second timeout condition lead to better accuracy because the 10-second timeout condition will introduce frustration so that they become less accurate because they're more agitated. What's going to happen? We don't know, so we're going to go with a two-tailed test. Now, here's the data that they have, and the important part of this is to realize that every single participant gets measured twice. That is the key feature of the dependent means t-test. And what that means is that we have 2 scores for participant A. We have how they did in the 5-second timeout condition, they have 71% accuracy, and how they did in the 10-second timeout condition, they have 86% accuracy. 2 scores. This is the first time we're dealing with a experiment where we have 2 scores for every single subject. So for subject B, we have their 5-second accuracy, 68%. We have their 10-second accuracy, 80%. For subject C, 5-second accuracy, 91%, 10-second accuracy, 88%. And we have this for all 9 participants. So that is the first important thing to realize, is that in a dependent means t-test, every single subject has 2 scores, one for condition A, one for condition B. So here we have 1 score for the 5-second timeout condition, 1 score with the 10-second timeout condition. So in this case, for the hypothesis test with the dependent means, it has the same structure that we've been dealing with so far. It has the same structure of taking a sample from an unknown population. However, the big difference here is that for the first time, and this makes a ton of sense, for the first time, we're going to measure this sample before treatment, and then we're going to measure them a second time after treatment. So we're going to measure them before we do anything, and then we're going to measure them after we do anything. We're going to measure them twice. In this case, for this experiment, we're going to measure them in the 5-second timeout condition, and we're going to measure them in the 10-second timeout condition. We're going to measure them twice. So this is the first time this is happening. So we're going to have to tweak the t-test just a little bit so that it is appropriate for this situation that is called dependent means. And it's called dependent means because the means, the sample mean for one condition and the sample mean for another condition are dependent on the same people. So the 5-second timeout condition here, the sample mean for the 5-second timeout condition is dependent on the scores of participants A, B, C, D, all the way to I. The 10-second sample mean is also dependent on the same people. So that's what we mean by dependent means. Both sample means are dependent on the exact same people. So we're measuring every single subject twice. And the reason that this is part of the single sample t-test chapter is that because they're from the same subject, what we're going to be doing in effect is we're going to be analyzing the difference scores. So this entire procedure works as if we have calculated difference scores. We have calculated the 5-second timeout condition accuracy minus the 10-second timeout condition accuracy to come up with one difference score of accuracy. And in effect, what we're going to end up doing is we're going to treat those difference scores as a single sample t-test with a difference score mean and the size of the difference score sample. But in effect, what we're going to end up doing is we're going to end up treating it as a single sample t-test. And that's why these two t-tests, single samples and dependent means, are grouped together. So that's what we're going to be doing in effect. However, we're going to be using SPSS, so we're never actually going to be able to see that. We're never actually going to kind of visually see it or visually calculate it. All of that is going to be done behind the scenes by SPSS, but I just want to peel back the curtain a little bit so that you know what's going on. All right, so it's a dependent means t-test. What does that mean about our 5-step procedure? Well, it means the 5-step procedure stays exactly the same. This is the 5-step procedure for hypothesis testing in general. Now we're going to do it for dependent means, but we're still going through steps 1 through 5, and they're still the same steps. So let's start off with step number 1. Restate the question as a research hypothesis and a null hypothesis about the population. We want to know, is there a difference in the accuracy between the 5-second timeout condition and the 10-second timeout condition? Is there a difference in accuracy between those two conditions? Our research hypothesis is that there is a difference in accuracy. We don't know if 5 seconds is better or if 10 seconds is better, but our research hypothesis is that time does have an effect. So there is a difference in accuracy between the two timeout periods. So we're going to write this as the mean, the population mean for the 5-second population does not equal the population mean for the 10-second population. So that will be the treated population. If that 10-second condition is different, that means that people living in a population where they are put into 5-second timeouts are completely different than people living in a population that are under 10-second timeouts. That's what this research hypothesis is saying. The opposite of that is the null hypothesis. So the research hypothesis is that there is a difference in accuracy. The null hypothesis is that there is no difference in accuracy. And in this case, the mean accuracy for the 5-second population is going to equal the mean accuracy for the 10-second population. And really, all of these people, 5-second timeouts or 10-second timeouts, belong to the same population. They have the same accuracy. So that's the null hypothesis and the research hypothesis. And that's the same as what we've been doing before. Null hypothesis, the two population means are the same. Research hypothesis, in this case, two-tailed, the two population means are different. All right, step number 2, determine the characteristics of the comparison distribution. If we did this by hand, this would be a massive mathematical undertaking. Thankfully, however, we're using SPSS. So SPSS is going to do this, and we don't have to peek behind the curtains in order to be able to do our dependent means t-test. Step 3, set a cutoff sample score or a critical value. SPSS is not going to do this for you. So this is one area of the hypothesis test that is not built into the SPSS output. However, it will help. Once again, it will give us the degrees of freedom that we need to look for. So just be aware that you are going to have to look up your cutoff score if we continue to use cutoff scores to make our decisions. However, we are now going to start our transition away from setting cutoff scores. So you already know how to look up a cutoff score in the T table, T statistic table. You already know that you need the degrees of freedom, and you need the one-tailed or two-tailed, and you need the alpha level to zone in on that cutoff score. But that means that you cannot do this entire hypothesis test using SPSS. You have to go to an outside source. And we really want to start developing the skills so we got one-stop shopping. So we can just do SPSS and use that to make our conclusion in step 5. So what we're going to do is we're going to start moving from cutoff scores to cutoff probabilities. And we can do this because, as you recall, in a distribution, a score is directly linked to a probability. If you have a probability, you can go to your t-test table and look up a cutoff score. If you have a cutoff, and in fact, that's what we do when we take the alpha level and look up the cutoff score for that alpha level. If you have a cutoff score, you can figure out a probability. So these two are interlinked with each other. They are basically translations of each other. So cutoff probabilities, those are given to you in the question. So we are going to use that from now on instead of a cutoff score. In your homework, you're still going to have to look up a cutoff score. So you're still going to have to go to that t-test table. But to prepare you for doing this in the real world, and so that we can have that one-stop shopping with SPSS, we're going to start moving to a cutoff probability. And the cutoff probability that we're looking for is basically one of the easiest parts of this hypothesis test now. Instead of having to go to a table, you go straight to the question, because your cutoff probability is your alpha level. So in this situation here, in this hypothesis test, instead of looking at that 0.05 and translating it using the table into a t-test cutoff score, what we're going to do is we're going to bypass the table and we're just going to use that 0.05. So that 0.05 is now our line in the sand. That probability of 5% is now our line in the sand, and we're going to use a probability line in the sand in order to make our final decision. All right, so step number 4, determine your sample score on the comparison distribution. SPSS will do this for you. So that is very nice that they'll do that for you. They will do your sample score. However, notice that we are now dealing with cutoff probabilities rather than cutoff scores. So not only do we need to find our sample's score on the comparison distribution, but we need to translate that score into our sample's probability on the comparison distribution. So we're going to find out how to calculate that, or how to look up that sample score, that sample T statistic on the cutoff, on the hypothesis test. But we're also going to find out how to find that sample's probability, because again, remember, T statistic and probabilities, they're linked. So you can translate one into the other. Step 3 is going to give us a cutoff probability. If we want to compare something to it, we need our sample's probability, and that is the p-value. So the p-value is literally the probability of your sample occurring if the null hypothesis was true. More importantly, it is what you compare. It is the number you compare to the number we have in step 3. It is a number you compare to your cutoff probability. And most importantly, SPSS will calculate this p-value for you, making it completely unnecessary to go to the table, the t-test table, at all. So that's step 1 through 4. What we're going to do right now, all right, so we are now going to go to doing this with SPSS. The Excel sheet that you need for this is week 13, class 1, practice chapter 8, introduction to the t-test. And as usual, we have screenshots in the PowerPoint files so that you can use that to sort of see see how to do that in still images. We also have this video that you can use to play back at your own pace. But just to kind of show you what we're dealing with, this is the Excel sheet that you want. So here, chapter 8 in class practice, and this adult timeout data is what we're going to need. So as usual, in order to use SPSS, the first thing we want to make absolutely sure that we have is we need that raw data. In order to run SPSS and use SPSS, you can't just have the sample mean. You have to have the raw scores for each individual, and that's what we have presented here. So let's get going with SPSS. I've already opened up my SPSS. If you haven't already, this is a good time to pause the video and go into 1IU and make sure that you have that SPSS opened. But mine is already open, so pause the video, open up SPSS, come back and join us, and we will get underway with using SPSS to do the dependent means t-test. All right, so the first thing we're going to do is we're going to close this welcome box. Again, it has a lot of useful information, but nothing that we need right now. So we're going to do a couple of things here. We need to move this data into SPSS. And the first thing that I'm going to do, and this is unnecessary, but I'm going to do it to show you a couple of features of SPSS. We're going to move in the labels that we have for each participant into SPSS. So we call these participants participant A, B, C, D, E, F, G, H, I. So we're going to copy that, and we're going to go to SPSS, and we are going to paste that into row 1, column 1. And you can see here, let me just stretch that out a little bit for you. You can see here that SPSS has named that row of letters var 00001. Horrible name for human beings. Horrible name for the human mind. Excellent name for a computer. If you're a computer, that would make complete sense to you. We're humans. It doesn't make any sense to us. So we're going to go down here to variable view, and we're going to click there at the bottom of the screen, and we're going to highlight this variable, and we are going to call it person. All right, so we're going to rename this variable as person. I don't want to use participants because that is more than 8 characters long. And as I mentioned in the previous video, name your variables 8 characters or less, and you will always be safe. Name them longer than 8 characters, and you take your chances. So it's probably going to be okay if we put in participants, but let's get into that habit of just calling it an 8 character or less name. Now, the other thing I want to point out is here in this second column, you'll see that that second column is type. And this is where SPSS stores what type of variable it thinks that you're using. And the big distinction that we need to understand, and the only difference that is really going to make, really going to have an impact on our hypothesis test, is the difference between a variable that is numbers and a variable that is words. This is very important SPSS because you can do certain things with numbers that you cannot do with words and vice versa. So SPSS will try to classify your variable as either consisting of words or consisting of numbers. So what we have here is we have our person variable, which is a series of letters. And SPSS has said, oh, okay, it's a series of letters, so I'm going to call that a string variable, aka I'm going to call that a word variable. So this is very important because SPSS will not allow you to do certain things like a dependent means t-test if you have a word variable. So I put that in here for two reasons. One, to illustrate the idea of the word variable. Two, because now for the first time, we have more data that we have to put into SPSS. So the question becomes, where does this data for 5 seconds go? Where do we put these particular scores? And the reason that I labeled those rows as A, B, C, D, all the way up to I, is that the organizing principle, the main organizing principle for data in SPSS is that every single row is reserved for one and only one subject. So row number 1 here is reserved for subject A, and subject A's scores can only go into row number 1. So when we look here at our Excel sheet and we have an accuracy score for the 5-second condition for subject A, this score of 71%, that has to go somewhere in row number 1. So we can click on row 1, column 2, we can paste in that information, and now this is properly formatted. So far, we still have one more set of data, but this is properly formatted. And we're going to want to go and rename this variable, and we're going to do that right now. But just to reiterate it, and I'm going to reiterate this over and over again, every single row in SPSS is one and only one subject. So all of your data for any particular subject has to go on the same row. So subject A does not get 2 rows for their data, has to all go on 1 row. So now we got this var 00002, horrible name. So we go back down to variable view, and we're going to rename this. And my human brain would say to myself, this is the 5-second condition, so I'm going to rename this 5 seconds. Now, we're not going to put any spaces, because as we learned last time, SPSS is not like spaces, but I'm going to call this 5 seconds because that to my human mind makes sense. So I rename it 5 seconds, I click away, and lo and behold, SPSS says, no, I don't like this. And it lets you know. So it gives you a warning, but it lets you know what's wrong. It goes variable name contains an illegal first character. So we learned a little something today. SPSS does not allow you to start a variable name with a number. So 5 seconds is not okay. So instead of doing that, let's use our human problem solving skills and saying, all right, instead of 5 seconds, how about seconds 5? Right? So we got seconds, S-E-C-O-N-D-S, that's 7, 5 is 8. We're within that 8 character limit. Let's see if SPSS likes this one. Yes, it does. Whoops. Yes, it does. So SPSS is fine with us calling this seconds 5. Now over here in the type, you can see now in row 2, SPSS has said, oh, this is not a string variable. This is not a variable that is supposed to be a word. This is a numeric variable. You're giving me numbers. And because of that, it's going to allow you to do certain things with your 5 seconds variable, your seconds 5 variable, that it's not going to allow you to do with the person variable. Like, for instance, take an average. All right, so we have those two variables set. The last thing we need to do is we need to import or copy our final variable here. Now I'm going to do this incorrectly just to show you something to begin with. So we're going to copy this, and notice that I have copied the header as well as the data. So not only have I copied all the scores, but I've also copied the label for this variable, that label that indicates that it's the 10-second variable. And this is something that you'll probably do. You'll probably make this error every once in a while. But let's see what happens when we come in here and we paste it. So when we paste it, SPSS is fine. It'll say, all right, I'll take that data. But notice what it's done. It's, number one, the data doesn't fit. So almost immediately, we're going to realize that, oh, we made an error. But importantly, look at this variable number 3 up here. SPSS has made a decision that you just gave it, if you see row number 3 here, you just gave it a whole bunch of words. So because it contains one score that is not a number, SPSS has decided that all of those entries are words. So this 10-sec, SPSS is considering that a word. And this 86 over here, that's not the number 86. That's the word 86. This 80 right here in the third row, that's not the number 80. That's the word 80. So if we were to leave our data like this, later on, SPSS will say things like, you know, well, I don't know, I can't take the average of this variable. I can't use this in my dependent means t-test. So that's going to be an issue later on. So what we might say to ourselves is, all right, well, we have the data there. Let me just copy that and I'll paste it up here, right? And I'll delete this last little 76 right down there. And now it should be fine. Now we have a bunch of numbers, right? Wrong. You go back to row 3 over here, and you'll notice SPSS has not changed its mind. And it is very difficult to make SPSS change its mind. It has decided that this variable is a whole bunch of words. And there's a way to do it, but it's very difficult. So what we're going to do is we're going to do it the easy way. And we are going to go back here. We're going to highlight that entire column, and we're going to hit delete. And we're just going to get rid of it. So we highlight that whole column, we hit delete, we start over, we go back to our Excel sheet. All right, we go back to our Excel sheet. Where'd it go? There it is. We go back to our Excel sheet. We only highlight the numbers. We only copy the numbers. We paste these into SPSS. And now look what SPSS has done. We'll go to variable view. SPSS has said, oh, okay, whole bunch of numbers. This is a number. So that's what you need to do if you ever make this error. Just delete the entire column. Just click on the column header, delete the entire column, start over, and now we can call this second 10. Whoops, no space. Now we can call this second 10, and now we're going to be completely set up, and we have everything formatted the way that we need it formatted. So we have it all formatted. Again, all the scores for A are in column 1. All the scores for E are in column 5. All the scores for each subject are in its own column. So now we're ready to go on the hypothesis test. To do the hypothesis test, once more we go up here to the menu to Analyze. And once we click on Analyze, we go down to Compare Means. And then once we click on Compare Means, we're looking for the correct t-test in this menu over here. Now, last time we did this, SPSS was very friendly. We were doing a single sample t-test, and SPSS had a one sample t-test that it was, I called it a one sample t-test. In our human minds, that makes sense. Single sample, one sample, same thing. SPSS is being friendly. Here, SPSS is not being friendly because we're looking for dependent means t-test, and there's nothing that makes our human minds think that we see dependent means t-test or anything like it. So make a note of this. The test we're looking for, SPSS calls it paired samples t-test. So the dependent means t-test is the paired samples t-test. That's the selection you're going to want to make for a dependent t-test. So make a note, write this down where you need to. Remember that when we're doing a dependent means t-test, in SPSS, we have to select paired samples t-test. All right, so we select paired samples t-test, and you're going to see here that SPSS says, all right, you have seconds 5 as an available variable. You have second 10 as an available variable. But note, it doesn't even give us the option of person as a variable. And that's because SPSS has classified that as a word variable. It's classified it as a string variable. So if you're ever doing this t-test and you don't see one of your variables available to continue with the t-test, chances are it's been classified as a word. And you're going to have to go back, delete that column, and fix that before you can proceed. So here we have our 5 seconds and our 10 seconds. And what we need to do is we need to move those into this variable, into this paired variables window here by clicking on one of them and then just pressing the arrow and moving it into the variable 1 position, clicking on the other one and moving it in here and moving it into the variable 2 position. So let me just stretch that out so we can see which ones are in which. So we got the 5-second variable as variable 1. We got the 10-second variable as variable 2. Now we can put these in a different order for the second pairs. So let's take a look at that and see what happens. So it matters which one goes in first and which one goes in second, because SPSS will take one of those and subtract it from the other one. So you can either take 5 seconds minus 10 seconds, so the 5-second accuracy minus 10-second accuracy, or you can do the 10-second accuracy minus 5-second accuracy. In the end, you're going to come up with the same answer. It's just that depending upon the way that the question is phrased, such as was there an increase in accuracy, was there a decrease in accuracy, it might make a difference whether you'd put one in or the second one. Not for the final answer, but just for our own human understanding. In this case, we were just asking if there was a difference. So that's going to be okay either way that we want to go. However, importantly, I'm going to do it both ways here. You don't have to, but I'm going to do it both ways just so that I can kind of show you the difference between the two analyses. So once we have 5 seconds and 10 seconds in as variable 1 and 2, we hit OK, and SPSS runs its t-test for us. So this is what this is the output right here. And what I'm going to do before we do our analysis here is just draw your attention here to this paired samples t-test table. And you can see that pair number 1 was the 5-second condition minus the 10-second condition. And the mean difference between accuracies was minus 7 seconds. What that means is that the 10-second condition is, sorry, it was minus 7%. What that means is that the 10-second condition was 7% more accurate than the 5-second condition. In this case, we have 10 seconds minus 5 seconds equals 7%. And what this means is that the 5 seconds condition was 7% worse than the 10-second condition. So in the first part here, we're seeing that the 5-second condition is worse than the 10-second condition. In the second pair, we see that the 10-second condition is better than the 5-second condition. Notice both of those are exactly the same. Logically, they're equivalent. The question you need to address is which one makes more sense for your human mind. And if one of them makes more sense than the other one, make sure that you choose the t-test that is in the right order so that your brain can make sense of it. So if 10 seconds is better than 5 seconds works for you, set up the t-test so that it's in that direction. If 5 seconds is worse than 10 seconds works better for you, set it up in the opposite direction. So what I'm going to do so that we are consistent with what we have in the slides here is I'm going to close this down, and I'm going to go back here to analyze compare means, paired samples t-test, and I'm going to get rid of this second pair over here because that's the pair that was not in the slides. So just so that we have the same sort of output as we do in the lecture slides, as we're going to talk about in just a second, I've done it this way. So this is what we're going to be working on. But again, you have the ability and you have the power to reverse that direction if you see fit. So let's take a look at this output right here. So again, this is formatted slightly different, but it's in the same order. It's got the same structure. So don't worry about the fact that there's extra lines here and they were taken out in later versions of SPSS. This is the output that we have. So we are all done with our analysis. And what we need to do right now is we need to interpret and read from this table steps 2 through 4 so that we can then do the final step, which is step 5. Now, previously, step 5 was we decide whether or not to reject the null hypothesis. And previously, we had sample scores and cutoff scores, your sample t-score and your cutoff t-score. And if the sample t-score was beyond the cutoff t-score, we would accept the research hypothesis and we would reject the null hypothesis. And if the sample t-score was within the cutoff t-score, we would accept the null hypothesis and we would reject the research hypothesis. These two slides are going to be very important for your homework, because in your homework, you're still using cutoff t-scores and sample t-scores. However, moving forward, so that we do this the way that it's done in real life, we're going to translate the t-scores into probabilities. We're going to translate the sample t-score into the sample probability or p-value. We're going to translate the cutoff t-score into the cutoff probability or alpha level. So these two slides become, if your p-value, your sample's probability, is less than your alpha, your cutoff probability, you accept the research hypothesis and you reject the null hypothesis. On the other hand, if the p-value is greater than alpha, accept the null hypothesis and reject the research hypothesis. So these two slides might not make sense to you right now, but rest assured, they are exactly the same as the two slides that we've been using. They will lead you to the exact same answer as the two slides we were previously using with cutoff scores. They're the exact same logic. So this is going to be the way that we're going to use it. It's much more streamlined. We don't have to go to the table. So this is how we're going to handle step 5. All right, so back to the output. Let's zoom in on that a little bit so we can see it a little more clearly. So the first thing we're going to do is we're going to take a look at that top table that says paired sample statistics. This is always your first stop whenever you do a hypothesis test in SPSS, because this is where you double check to make sure that you even started with the right data. So we can calculate means for each of these scores in Excel and then compare them to the means in our SPSS output. And the 5-second condition should have an accuracy of 76.1. And SPSS is saying, yeah, that's the accuracy that it has. And the 10-second condition should have an accuracy of 83.1. And SPSS here is saying, yeah, that's the accuracy we have. So that gives us confidence that we copied and pasted correctly. More confidence that we copied and pasted correctly comes from that column right there labeled N. That's the number of scores that SPSS has in each condition. So it's telling us, I analyzed 9 subjects in the 5-second condition. And we double check and say, yeah, that's how many you were supposed to have. And SPSS says, I analyzed 9 subjects in the 10-second condition. And we check ourselves and say, yeah, that's what you were supposed to have. So again, it just gives us confidence that we have done this analysis correctly, or at least entered the data correctly. All right, step number 2, determine the characteristics of the comparison distribution. So SPSS is going to do this for us. What we need to find for this is we need the degrees of freedom and we need the estimated standard error. We need the degrees of freedom and we need that estimated standard error, that standard deviation of our comparison distribution. This is one of the first times where we have standard error mean in a bunch of different places. So there are 2 numbers in that top table in the column labeled standard error mean. And there is 1 number in the bottom table, that paired samples t-test table. There is 1 number there that is labeled standard error mean. So the question is, which one do we look for? Which one do we look at? And the answer is that one. So make a note. That's the standard error of the mean that you want. So be very clear and be very deliberate and know the standard error of the mean that you're looking for. Know which one of these is the correct one for the comparison distribution. And in this case, it's in that bottom table, and it's the one labeled standard error of the mean, and it's got a value in this case of 2.0. So that is the standard deviation of the comparison distribution. The next thing we need for the comparison distribution is its degrees of freedom. This one is a lot more friendly for SPSS because there's only one thing in this entire output that is labeled DF, or degrees of freedom. So SPSS is letting us know we have 8 degrees of freedom. So the comparison distribution has a standard deviation of 2, that's the estimated standard error, and it has 8 degrees of freedom. So set a cutoff score, sample score, or critical value. SPSS will not do this, but it will help. And the way that it helps is it lets you know how many degrees of freedom you have. So SPSS lets you know that we have 8 degrees of freedom. So we can go to the table that we've encountered, the cutoff scores for t-distributions, and we can go through the process now knowing that we have 8 degrees of freedom. So we can go through the process and say, all right, this is a two-tailed test. We have 8 degrees of freedom. The alpha level is 0.05. So where all that intersects is a cutoff score of 2.306. So this is for your homework only, because your homework is going to ask you for cutoff scores. We're moving beyond cutoff scores. We're going to move into cutoff probabilities. And it's important to realize that that cutoff score has a cutoff probability. And in this case, you can actually see it on the table. That cutoff score is linked to a cutoff probability of 0.05 or 5%. And that's our alpha level. So instead of going to the table, we're just going to use a cutoff probability instead. And we're going to say, all right, we have an alpha level of 0.05. That's our cutoff probability, 5%, 0.05. That is our line in the sand in terms of our comparison distribution. So the next thing we got to do now, we're doing a step 4. Determine your sample score on the comparison distribution. SPSS will do this, and your homework's going to want to know that number. So we're going to show you where to get that number. But more importantly, we're going to also determine our sample's probability on the comparison distribution. And this is that p-value. This is that all-important p-value that we've mentioned before. This is the probability of getting a sample this weird if the null hypothesis was true, if there was no effect, and SPSS will do this. So let's take a look at first how to find that sample score, and then we'll look at the sample probability. So the sample score is your sample mean as a t-statistic. So this is the pair that SPSS was looking for. Those are the two variables that SPSS was comparing. And the mean difference between those two is listed right there. So that tells us that there's a 7% difference between the 5-second condition and the 10-second condition. That the 5-second condition is 7% worse, that's why it's -7, 7% worse than the 10-second condition. And that mean difference combined or divided by the standard error of the mean, or the comparison distribution standard deviation, will give us our t-statistic. So we could do the math there, or we could just let SPSS do the math and read off the input. So that column labeled t, that is your sample's t-statistic. That is your t-statistic for the mean difference. That's the t-statistic that you need to report in a real-world situation, or more importantly, immediately for your homework. So that's where you can find your t-statistic. However, we're going to move away from t-statistics to probabilities. So now we need to figure out, well, what's our sample's probability on this comparison distribution? That is, given that t-statistic, if I asked you, find the probability in the tails associated with that t-statistic, that's the probability of your sample. So that would be very difficult to do given the table that we have. So thankfully, SPSS will do this for us, and we just need to know where to read it. So as we take a look at our table here, we take a look at probability. Usually it's labeled significance or sig. And once again, SPSS is being a little tricky here, because if you take a look at that middle table, paired samples correlation, it's got a column labeled sig. But if you take a look at the bottom table, it also has a column labeled sig, but then in brackets two-tailed. That bottom table one is what you want. That's the number that you want. So don't get fooled by the middle table. Completely ignore the middle table. What you're looking for is that bottom table column labeled significance, two-tailed, and the probability of our sample occurring is 0.008. So if the null hypothesis was true, getting a difference this large will happen 8 in 1,000 times. Pretty unlikely. So now the final thing we need to do, now that we have the p-value, is we need to do step 5. And normally we would compare the sample t-score to the cutoff t-score, and if the sample t-score was beyond the cutoff t-score, we would accept the research hypothesis and reject the null hypothesis. If, on the other hand, the sample t-score is within the cutoff t-score, we would accept the null hypothesis and reject the research hypothesis. So we have a t-score of -3.5. We have a cutoff score of 2.306. So according to those rules, our t-statistic has gone beyond our cutoff score. So remember that cutoff score is plus or minus. So our t-statistic for our sample has gone beyond our critical t-statistic, our line in the sand, and therefore, according to the rules that we have, we reject the null hypothesis. That's a conclusion we come to using the t-statistic and the cutoff t-score. What's the conclusion that we're going to come to using probabilities? So the rules again are, if the p-value, if your sample's probability is less than your alpha, accept the research hypothesis and reject the null hypothesis. If on the other hand, the p-value, your sample's probability is greater than your alpha level, accept the null hypothesis and reject the research hypothesis. So our p-value, our probability of our sample was 0.008. So we have a p-value of 0.008. We have an alpha level of 0.05. Our p-value is less than our alpha value, so we reject our null hypothesis. And notice that this is the exact conclusion that we came to when we use the cutoff scores. And that's because cutoff scores and probabilities are directly related to each other. So all that work that we did on the normal distribution and finding the proportion in the tail, that's all paying off right now to help us understand that this analysis and this analysis, exactly the same thing, both came to the conclusion that we reject the null hypothesis. Both allowed us to conclude that a 10-second timeout period actually is better or leads to better accuracy than a 5-second timeout period. So bottom line, timeout works for kids and it also works for adults. All right, so that was the hypothesis testing with the t-statistic for the dependent means. Just a couple of reminders before we wrap up today. You continue working on your pretest, continue working on the MyStatLab study plan, especially now as the pretests are getting more challenging. This is going to be a very important aspect to make sure that you can maintain that high GPA if you want, that you're not getting punished for the difficulty of the pretest, because you can still get 100% by completing the MyStatLab study plan. And then also there is extra practice for today's lesson, and that is found in the supplemental week 13 class 1 practice, chapter 8, introduction to the t-test PowerPoint. And the numbers for the raw scores for that are available in the Excel sheet that we've been using so far. So I would highly recommend give those a shot. They come with the question, the output that you're looking for, and then the interpretation of the 5 steps that you're looking for as well. And just to let you know, you are now ready to do homework assignment number 11, chapter 8 homework part 2. So this is the part 2 version of the homework where we look at the t-test for the dependent means, and that's going to be due April 9th by midnight. All right, so that is it for today's class. So that was the t-test for dependent means. We got one more version of the t-test that we're going to be taking a look at next class, but there we have today's lesson. So once again, thanks for joining me. Can't wait to see you next time, and stay safe out there, get your practice in, and I will see you next time.